So our next speaker is Enjin Kim from the University of Sheffield, who's going to talk about the theory of turbulent transport and dynamos in astrophysical plasmas.
Thank you. Under this very vague title, I'm going to present some of the recent work that I have been doing my postdoc, Nicola Reprobos at Sheffield, trying to understand some of the outstanding problems in astrophysics, mainly the momentum transport and the dynamos. And we see the magnetic field and the shear flow, such as the rotation and the differential rotation, in many objects, including astrophysics. So the understanding the origin and the evolution of these structures has been very difficult. I mean, interestingly, the evolution of these two objects is closely linked by dynamo process and the spin-down process. So first of all, magnetic fields can be generated by dynamo processes which involve the alpha effect and the shearing, which I call the little omega here because I'm going to use capital omega for global rotation. So for instance, the efficiency of alpha omega dynamo is roughly measured by the dynamo number, which has the product of the alpha and the omega effect. Here the delta omega is the differential rotation divided by the turbulent diffusivity square. So if you just look at some of the textbook, and then you may be able to put out some kind of estimate for the alpha and the differential rotation for different rotation rate. For instance, alpha, both of them are proportional to rotation. Why is that? Because you envision the generation of alpha effect through this helical motion if you trust in alpha effect in the first place. While the second relation is very questionable, and there has been a lot of observation trying to understand the relation between the differential rotation and the rotation. But this is kind of estimate that people normally use. And the estimate for turbulent diffusivity beta is kind of very suspicious, but they normally use that the beta effect is unaffected. Therefore, it is just turbulent value. If you use this estimate, then you can boil down the dynamo number to this expression which grows quadratically with the rotation rate. Or you can say this is inversely proportional to the Rossby number. So for high rotation, for small Rossby number, you will expect very strong driving for your dynamo. So this is part of the story why the differential rotation or rotation is important for the generation of magnetic field. And the other side of the story is that the magnetic field are also linked to the evolution of rotation by magnetic braking. Meaning that when stars are formed, they are a fast rotator, and during the course of the evolution, they spin down a lot. And this spin-down process is helped by this magnetic field removing the angular momentum from the surface. So if you want to understand the evolution of the various different stars in this HR diagram, you really need to understand the link between these two processes. The evolution of the rotation is momentum transport, while the evolution of the magnetic field is the dynamo. Is related to the dynamo process. Right, so here I'm going to show one example showing the link between the magnetic field and the rotation of various different stars taken from Cardini and the Castel-Tella 2007 paper, which I forgot to write here. So just let us focus on the second panel, which shows the magnetic activity measured by the magnesium 2K surface flux as a function of the period. So this end is the high rotation, slow rotation, and as you go this way, this for high rotation. So as you can see that you have strong magnetic activity as the star rotates faster. And however, you may know, there is a dispersion in this plot because these stars are taken at different ages, so there is different types of stars, so there is also dispersion. However, you can see the tendency of increase in the magnetic activity for fast rotator, which tends to saturate for high rotation rate. So one of the interesting questions is how this saturation occurs for high rotating star. And one promising mechanism is that, which is usually invoked, is a dynamo process somehow saturates for high rotation. That can be via the magnetic back reaction or also for the saturation of alpha effect for the fast rotator, as I will say later. However, now if you want to, this is one possible mechanism, but the different stars come with different physical properties. So if you really want to understand the whole spectrum, then you really need to understand how this alpha and beta effect depend on different properties, such as the rotation, magnetic field, and also the differential rotation and stratification, etc., etc. So here are some of the properties that may vary from the star to star. So here are the three, the first three, rotation and magnetic field and then stratification, have this common ground, which is that they all excite the waves. So if you have a rotation, you may have the extension of inertia or the Rossby waves, and the magnetic field size alpha waves. And if you have stably stratified medium, you will have the gravity waves generated. So the one property of the waves is that they reduce the turbulent transport. So what I'm talking about is that you envision a system which is turbulent, which drives the fast turbulent transport. Then you can imagine putting this turbulent system into the stable medium where you rotate or you put the magnetic field. What happens is that the transport is reduced because what happens is that for the transport, you need some sort of stochastic or randomness in your system, which your turbulence provides. However, now once you excite the waves in the system, the waves make the turbulence kind of very coherent. So they reduce the randomness or stochastics, which was crucial for turbulent transport. So they all have the tendency of reducing transport. And you have heard about the alpha quenching or beta quenching by magnetic field, and that is one magnification. And the rotation has a similar effect, while you also know that the rotation is important for the dynamo through the alpha effect. So what happens is that you need a rotation to generate some flow helicity for smooth rotation. However, once you have strong rotation, this rotation excites these waves which have become strong, so you have kind of tendency of reducing transport, the alpha effect. So what happens is that as you increase the rotation, your alpha effect increases, and then it finally saturates. So it tends to reach some constant value. And when you have this stable media, you will have a similar reduction in the transport by gravity waves, and there have been a lot of numerical simulation looking at the effect of stratification, the transport of particles. So I guess I got distracted a lot. But the main focus of this talk is looking at the effect of differential rotation on transport. And for the complete story, we need to combine all of this. So what you have is kind of wave plus turbulence plus shear flow. So you need to kind of incorporate all this interplay between different animals to really have the full understanding. So let me just comment on the effect of shear flow on turbulent transport. So here is the same story. To the zeroth order, you have turbulent medium which mediate very fast transport. And then what you want to do is just impose the shear flow on top of the turbulent media and see what happens. What happens is here is kind of a cartoon picture. So here this circle is the turbulent eddy, which makes things very efficiently on the advective time scale. And then you have this imposed shear flow, and what this shear flow does is advect these turbulent eddies at different rates. So the top part will go to the right more than the bottom part, and this process will continue until it reaches small scale where the dissipation becomes important to disrupt the eddies. So this process will continue, and the overall effect is the enhancement of the small the speeding up of the small scale generation, which is easily destroyed, quickly destroyed on small scale. So this is, so what shear flow does is effectively enhance the dissipation of the system, reducing the turbulence amplitude. In addition to that, it will also reduce the transport because, and you see, you have the big guys sitting here, but that gets very small. So effectively, the correlation length becomes small as well as correlation time of your turbulence. So you have the reduction in both turbulence and transport by shear flow. The waves also have the effect of reducing transport, but the waves do not necessarily alter the turbulence amplitude. You have alpha turbulence, and you may still have a vigorous amplitude. But so there is a difference between the waves and the turbulence. But I just need to acknowledge my Andrew Newton, who produced this figure. This is not it's not the plot that I made. And let me just comment that this process has not been studied much in astro context. However, it is now very recognized to be very crucial for fusion plasma, for instance, for the plasma confinement, and also it has been invoked in the mixing in the ocean and the atmosphere. Right, so the key issue here is what is the interplay among shear flow, turbulence, and waves? And the traditional solar modeling use some sort of estimate. All the transport coefficient is order of velocity times the correlation length of the turbulence up to some constant, and then the constant is according to what you want from observation. And the interplay between the turbulence and the interplay between waves and shear flow have not, and the waves and the turbulence has been incorporated consistently. Physically, what happens is that this V or L will become a dynamical quantity depending on what kind of wave you have or how strong your shear flow is, and etc. So this VL or the correlation time are not the free parameter that you can play with. And the other consequence is that when you have shear flow or these waves, you may end up with some anisotropic turbulence as well as transport.
Sorry, when you speak about shear flow, the glass shear is very strong in comparison with the turbulence time?
Yeah, if you make your shear flow, you won't do much. This is kind of extreme limit where your shear flow is very strong. So for the remaining part, I will consider where shear flow is, yes, shearing rate is larger than the inverse of the correlation with time. Right, so what I'm going to do is briefly summarize what we have found in the hydrodynamic turbulence with different waves, and then I'm going to discuss what is going to happen for the dynamo process. So here, the simplest hydrodynamic turbulence that you can think of is just Navier-Stokes turbulence plus the shear flow, the shear turbulence. So what the main result is that the shear flow now, I'm going to take explicit form, which is a linear shear flow with a shearing rate A. I'm reserving omega for the rotation, the later. It's just a linear shear flow. And if you have the strong shear flow, then you will catch the both turbulence amplitude and the transport. And it also will decrease the effective correlation time of your turbulence inversely proportional to the shearing rate. So if you make your shearing rate very strong, your turbulence will decorrelate very rapidly.
Not turbulence, transfer.
But no, the transport is a vector quantity. But it's, yeah. And also shear flow induces anisotropic turbulence and also transport. For instance, in the tapered line where you have strong or smooth shear flow varying in radial direction x, then we can assume the shear flow varies in radial direction pointing in y. Then you will then we get the turbulence amplitude in the radial direction much weaker than the other two directions. This is also true for the momentum transport. So even without having stratification in your tapered line, you can have the anisotropic transport and the momentum transport much faster in the horizontal plane compared to the radial direction by shear flow. Now the next one, you take the shear turbulence and then put it in the strongly stratified and the magnetized medium to mimic the tapered line more realistically. So what we have found here is that you will have reduction in the transport by shear flow and the stratification, which is due to the extension of gravity waves. But what is now different is that the momentum transports tend to be inverse. I mean, momentum transport is inverse. So you have the inverse cascade of the energy. So you will have the tendency of the generation of layer-like structure. And I'm not going into details. And the next one we look at is now you remove the magnetic field and the stratification and put it in the rotating system. Then now you will excite the inertial wave. And in this case, we found similar inverse cascade of the momentum, not only by the negative viscosity, but also through the non-diffusive momentum flux, which is called the lambda effect, which was studied by Gunther Rudiger and kind of 20 or 30 years ago. But what is new in this resource is that in the original work, that lambda effect existed when you have inhomogeneous background turbulence. And in our case, you can still have the lambda effect even if you have the isotropic forcing, because the shear flow induces anisotropy in the system intrinsically. Right, so I have 5 minutes to discuss alpha effect. So now this is main theme for the conference. So you remove rotation and stratification. So all you put it in the 3D and put the uniform magnetic field in parallel with the shear flow. So it's a simple turbulence system. So without any, the zeroth order system is just isotropic turbulence, isotropic turbulence driven by external forces, which is helical. So if you trust in alpha effect, this helical forcing will give you alpha effect for your for the generation of large scale field. So what we are interested in is what happens to this alpha effect when you put strong imposed shear flow in parallel with your magnetic field. So that is, and the way we did it, our computation was to use the time-dependent wave number to capture the shearing effect non-perturbatively. This method was used long ago, but in our earlier work we used some different theoretical method, which Sergei Lazarenko also used in his earlier work. And then we solved the quasi-linear equation for the linear equation for the fluctuation, and the justification is that when you have a strong shear flow, your turbulence becomes weak because of immense dissipation, and there has been some numerical work showing that this analysis gives good the prediction which agree with the numerical simulation, and my student is still working on some of the extension of those work. And once you solve the linear equation for fluctuation for a given forcing, then you can compute all the correlation function you want. And two correlation functions you are interested in is this electromotive force given the alpha effect and the momentum flux for your turbulent viscosity. And results shown here is obtained in the strong magnetic the strong magnetic field and the strong shear flow. However, the shearing is faster than the alpha frequency. So the shearing is the most dominant, and then alpha effect, and then the viscosity. So let us just look at what this guy do to the turbulence amplitude. Here again the axis direction along which the shear varies. And here psi is a small parameter measuring the viscosity effect to the shearing, which is small for the limit we are interested in. And V0 is the velocity amplitude when you do not have any magnetic field or any shear flow. So it is just the turbulence amplitude driven by your forcing in the absence of magnetic and shear flow. So the ratio between the two is given by this small number, meaning the shear flow reduced your turbulence amplitude. And you can see also that there is kind of anisotropy in the turbulence amplitude. So strong reduction in the direction where the shear flow varies. And the two results for the turbulent viscosity and alpha effect are written here. So what is now here is the turbulent viscosity in this limit is related to turbulent viscosity when you do not have a shear flow or magnetic field. So that is kind of zeroth order turbulence. And so when you have strong shear flow, your turbulent viscosity is reduced by a factor of psi squared, which is small for strong shear limit. So your turbulent momentum transport is reduced. That's the bottom line. And the alpha effect now is related to the kinematic alpha effect, alpha 0 sitting there, up to this factor psi to the 5/3, which is small, therefore. And there is the small correction comes due to magnetic field. So when you have to the zeroth order, you have a kinematic results alpha 0, and when you have strong shear flow, the overall amplitude is reduced, right? And then if you now take into account the magnetic field, the overall magnitude will be further reduced. So the alpha effect goes like the shearing rate to the minus 5/3. So those are two main results. So we have the quenching in both alpha and the momentum transport by shear flow. I mean, you can look at other limits where the alpha frequency is much larger than the shearing rate. In that case, you will have the dominant reduction in both turbulent momentum transport and alpha effect due to magnetic field. So here is the conclusion. So what I have shown is that the momentum transport and alpha effect are both reduced by the strong shear flow with this factor. And if you envision some renormalization process, you may just use the tau 0 here. And let us then look at what these results imply for dynamic efficiency, which we may need trying to understand the stellar evolution. So we are going to stick to the same estimate as before. So beta goes like velocity times the amplitude times the length scale. So if there has been any beta quenching also for the rotation, then this may be envisioned. And alpha 0 is the kinematic value, which we just use again from the textbook, and we again use and then we assume the untracked differential rotation is proportional to so differential rotation is proportional to the global rotation. Then what you end up is the dynamo number now becomes the tau 0 times omega to the 1/3. So it still increases with the rotation rate, but much weaker than we had before, which was omega 2 square, omega square. And in this estimate, I mean, there are a lot of uncertainty. First of all, the uncertainty is that how do you relate the differential rotation to the global rotation? For this estimate, I just used they are proportional to each other. But the recent observations show that the dependence is quite weak. It's like 0.2 or 0.3, and also the Postangrov and the Kikatinov have been trying to predict this differential rotation as a function of omega, also showing some very weak dependence. So if you hadn't used this estimate there, they will remove, they will make this rotation dependence even weaker, giving you a possibility for explaining why you have the saturation of magnetic activity for fast rotating star. So a mechanism, I'm not explaining everything. And as I said, there is a strong suspicion on the beta effect. So the beta effect should be studied self-consistently for this estimate. And by the end of the day, we want to put all this together to understand how various different stars behave over the course of their evolution for different mass and for different age. Thank you.
Thank you, Anjin. We have time for some questions.
Yeah, you have strong shear, so turbulence can be suppressed. Maybe it seems to me that there are problems with the applicability of mean field approach if shear is so strong. Is it correct or not?
Yeah, this analysis is good. Let me just show this slide. When you have a strong shear flow, you effectively enhance dissipation in the system, so they reduce the turbulence. So they tend to, the shear flow tends to give you weak turbulence. So that's how this analysis is good. And so there have been this work. I think this work was done in rotating turbulence, showing a good agreement in the prediction of the linear analysis with the shear flow with the numerical simulation. And the second work was to compare we made some prediction for passive scalar transport in shear flow, in shear turbulence, and they did a numerical simulation, and they found very good scaling agreement. And most recently, my student is looking at 2D MHD turbulence, verifying some of the predictions that we made a few years ago.
Here, rapid distortion series.
Yeah, that is another way of doing it, yes. Yeah. As Sergey also studied.
If possible, I would like to give a small practical comment. Your first correlation, which you describe, becomes much better if it is representing observational equivalent of rotational moment and magnetic moment. And then you can see from such a correlation that magnetic moment scales the square root of rotational moment. What exactly corresponds to the idea that Coriolis force is balanced by Lorentz force. It was described in the paper Baluna Sun and myself in APJ letters in 96, as far as I remember, and then it was developed.
The strong shear flow
this also can also be unstable, right?
Yeah,
and by development stability, develop its own turbulence.
Yes, that is,
so
yes.
on the one hand, it suppresses turbulence, on the other hand, it can enhance turbulence.
Yes,
so what happens in reality?
Yeah, I mean, that is very good point. I forgot to mention. I mean, yes, normally the shear flow is used to generate turbulence in astrophysical systems. So the star spins down and making because when star spins down, it throws on surface first. It generates the kind of differential rotation, and it may become unstable to shear instability, and then it generate turbulence. So I didn't discuss that part at all. This is the kind of opposite end of the story, which is varied only when the shear flow is stable. So what happens in reality, and actually this has been, there has been a lot of numerical simulation in the context of fusion plasma looking at how the shear flow evolves. So what happens is that there is a stage where this thing works. What I said is working. There is kind of regulation of the shear flow, regulation of turbulence by shear flow. And then, once the shear flow becomes strong enough, then it generates turbulence. So the whole thing just collapses. And so shear flow goes away, and then you have the kind of generation of, in 2D, you will, when you have like turbulence, you have inverse cascade, yes? So, the fusion plasma is most like a 2D because you have strong magnetic field. So when you have turbulence, you generate the shear flow. So what happens is that you have like a generation of shear flow which interact with the turbulence and self-regulating, and then it becomes so strong and becomes unstable and collapse, and then it builds up again during the process, during which this thing works, and then it collapses again. So by the end of the day, what I'm imagining is kind of some time variation in overall, in the overall evolution. And we had some work showing that the momentum transferred here again. In this stably stratified medium, you have like an inverse cascade again. So what happens is that in the topocline, you may have kind of a generation of the layer-like structure, making the differential rotation sharper in time. However, you will reach a point where your shear flow is not stable anymore. Despite the fact that it's very stably stratified, because according to the Richardson number, you will get unstable at some stage. But you will generate the turbulence, mix things very rapidly, and then you will once things settle down, then you will have a stable media, and then this process will continue. You will have generation of sharp structure, and then you will collapse, and then you will be done.
That's a good question.
Comment on this. What you said about this inverse cascade. If I understand right, you imagine sort of time-dependent process of generation of things and then collapse and so on. If I recall right, the picture I have is something, quite different in the sense of things not being time-dependent.
Yeah, inverse cascade alone means that if you have like a little guys, the energy tends, these little guys tend to form the big guys.
No, I understand.
Yeah.
So
that is part of the story.
Yeah, what I mean is, in a statistically steady state where something is being stirred or being generated, an example I can think of is, let's say, Rossby wave turbulence.
That's right, yeah.
Where you have, let's say, turbulence being generated from shear, okay, on some scale, and because of shear instability, and because of an inverse cascade, it grows to, there's some transport to larger scales, but that is again cut off on something called the Rhine scale because of the shear itself. So I think of it not so much as a sort of a time-dependent process, but more like scale separation. Waves are, energy is being injected at some scale due to shear instability. The scale increases because of an inverse cascade. And then there's a sort of balance between let's say, weak turbulence, putting things in the inverse cascade, and the shear cutting it off.
Maybe I can comment. There's some cases where you
Yeah.
do get this nice saturation and everything balances, but there are some cases where you do get like relaxation oscillations.
Like what you're saying, time dependent.
And collapses and then bursts and collapses.
Okay.
And to understand which one you get, you have to solve the nonlinear problem and
Okay.
just find out what happens.
Fine.
Thank you.
Okay, I think we better carry on. So sorry. I know, Nathan, you've been very badly treated.
But
You haven't asked any questions.
Then people know about the system a lot in meteorology.
Yes.
Yes, of course.
People should compare the result with meteorological people. Maybe it will be easy.
It's called the paratropic governor.
Yes.
Okay, our final talk before lunch by Peter Frick, who's going to be talking about the role of cross-helicity in stationary force MHD turbines.
My talk does not concern directly any dynamo problem. I would like just to discuss some properties of fully developed stationary force MHD turbines. The talk was prepared together with Irina Mizova, my PhD student, and Rodion Stepanov. So what I am discussing is the MHD of incompressible fluid, and in the frame of this problem, the more important thing is that the MHD equation have three conservation laws. So in the limit of small viscosity and magnetic diffusivity, the total energy, the cross helicity, and the magnetic helicity are conserved. Normally, it's believed that in the case of fully developed turbulence under very high magnetic and magnetic Reynolds number, the U and B fields are not correlated, and the cross helicity is close to zero and does not especially affect the turbulent flow. What about the third integral of motion? The role of magnetic helicity was discussed much more in the frame of the dynamo problem also. What I would like to discuss is the situation when in stationary force turbulence, together with the energy coming in the turbulence in large scale, some cross helicity, so some correlation, is stationary input in the turbulence. This problem was firstly discussed in the frame of the fact that the cross helicity, some high correlation of magnetic and velocity field were discovered in solar wind, and after that, in this paper, it was the first, to my knowledge, one discussed if this cross helicity, if this high correlation comes from the source of the turbulence, or it can develop during the free evolution of the MHD turbulence. In this paper, it was shown that in general, the cross helicity decays slower than the energy, and under free decay, the correlation coefficient, which is defined as the ratio of cross helicity as energy, grows with time. What about the first MHD turbulence? Different scenarios are suggested. So both of them are well known. This is the Hiroshnikov-Kreshnan law, which comes from the idea that the Alfvénic turbulence govern the turbulence. And the second possibility is the Kolmogorov-like turbulence, in which the kinetic and magnetic energy follows the five-state laws. In DNS, this scenario was observed by many people. And what about the Kreshnan-Hiroshnikov laws? It was observed, but in the situation when an external magnetic field exists, and just for the perpendicular component of magnetic and velocity field. concerning the first turbulence, the problem of influence of cross-correlation was considered in the paper of Grappin-Lerat-Fouquet in the frame of an ETQ-NM procedure, but concerning the Alfvéning MHD turbulence. Two main results were obtained. The first one, it was shown that in steady state, the ratio of cross-helicity and energy in the system becomes larger as the ratio of the input of cross-helicity and energy. And the second result concerns the spectral slope, which becomes steeper as the -3 half, which appear in this case in the uncorrelated state. Our goal is to consider the first isotropic, I mean Kolmogorov-like MHD turbulence with the stationary input of cross-helicity. So I start by some simple phenomenology. I suggest that the input of energy is equal to epsilon, and the input of cross-helicity, also stationary, is equal to He, and the equipartition is supposed, and the general suggestion of MHD, the spectral flux is constant, and some characteristic time of transfer at the given scale is T. For uncorrelated fields, the common suggestion is that this time is equal to turnover time of the vortex of given scale. The main idea in our works is what the correlation of magnetic and velocity field slows down the efficiency of the transfer, and this characteristic time is not more equal to the turnover time of the turbulence. It means that the vortex can be very strong, but due to the compensation of non-linear term, magnetic and velocity, the transfer is reduced, and this psi L is the coefficient which gives the ratio of the turnover time and of the characteristic transfer time and the turnover time.
Psi is larger than 1, right?
Yeah, it's larger than 1. So, for the energy of the given scale, we get this coefficient, which should change, and this coefficient can, of course, depend also of the scale. And what is suggested, that because the transfer becomes less efficient, the energy should accumulate in the system. So, and what's happened at each scale, the system can conserve more energy, and the total energy of the system at the given input of energy should be larger. So the turbulent accumulate the energy so that the growth of the intensity of motion can compensate the reduction of the efficiency of the transfer. For the largest scale, we suggest that this coefficient should be provided by the ratio of the input of cross-helicity and the energy, and because in the limit when he is equal to epsilon, this process should be stopped. It means that the energy should go to infinity. We suggest in the simplest form this dependence of this reduction coefficient of the ratio of the input of cross-helicity and energy. Then we get this simple formula which should estimate the total energy accumulated by the system in the presence of the input of cross-helicity. And what about the spectral slope? Of course, it will be connected directly with the properties of this reduction coefficient. So this simple idea will be confirmed in the frame of a simulation done by the shell model of MHD turbulence. So this is just to remind the basic idea of shell models. It's low dimension models in which for shell means a shell in K-space, in Fourier space, and for each shell one introduce few, one, two, sometimes a bit more variable to describe the fluctuation of velocity field or magnetic field in the given shell. And these models are quite efficient to describe the transfer process in the case of high Reynolds or magnetic Reynolds number turbulence. This is the general form of the shell model for MHD turbulence. And normally what we have used, and it's a model for the MHD turbulence, which is similar to very popular for normal turbulence, so-called GOI model. But the shortcoming of this model is with the helicity-like quantities are described in this way. It means with the quantities, the magnetic helicity, the same thing is for the hydrodynamical helicity in the case of normal turbulence. The positive and negative helicities are separated between the odd and even shells of the model. And this is why we have tried to modify this model, and we have constructed a new model in which the magnetic helicity is presented in this way, and so the advantage of that is that the helicity of any sign can be described in each shell. And what about the cross helicity? It's the same in both model. We have introduced this model special to describe the cascade of magnetic helicity, but just in this work, what I am discussing now, the magnetic helicity is supposed to be zero. But the model itself has some, I just will show some illustration. What does the model describe? This is the example of free decay. It's the old null result with the coefficients, the ratio of cross helicity and energy increase under free decay. So in the beginning it was something like 0.27, and with times it grows. The time is given in the large scale turnover time units. And this is just an example to show how the magnetic helicity cascade also can be described in the frame of this shell model. This is an example when the magnetic helicity is inputted near the K equal to 1, and this is the fluxes, the energy flux, the inertial range with direct flux of energy, and the well-pronounced inverse flux of magnetic helicity, which goes down to small k. And now what I'm discussing now is the stationary force turbulence. The input of magnetic helicity is zero, and the input of cross helicity is different in different situation. This is the basic case when the cross helicity, the input is also zero. In this case, the stationary situation, the stationary state arises in few turnover times, and in the second case, when the input of cross helicity is a half of energy input, we can see that the stationary state appears much later. So the typical time for this intermediate state is about 100, and the energy, the total energy given in red, much higher as in the case when it's no cross-helicity is input in the system. This is the change of spectral slope. This here is given the spectra compensated by the Kolmogorov slope, and for the input rate of cross-helicity 0.6, it's about 0.89. So for the E of k, it will be 1.89. And here is shown the spectral distribution of energy and of cross-helicity given in red, and also the inertial range, the flux, the constant flux of energy and cross-helicity is observed. Now, my main result I would like to show. This is exactly the formula proposed above and the result of numerical simulation. So this dependence of the total energy of the system accumulated at the stationary state. For the, I would like to stress again for the given power of force, and one can see what for the high cross-helicity input, the increase of energy is a factor of 100. So, and it follows well enough this simple estimation obtained from the general phenomenology. And the second graph, it gives the ratio of the correlation coefficient, the ratio of cross-helicity and energy at the stationary state is a function of the input of cross-helicity and energy. This result correlated well with the result obtained for the algebraic turbulence in the paper of Grappel et al. One can see what the level of accumulated cross-helicity is much larger as the input of cross-helicity in the stationary force turbulence. And the last slide concerns the properties. Just I would like to show directly how these characteristic types of energy transfer and cross-helicity transfer, because we have to suppose, and we see what it's so, that the flux of cross-helicity is also constant in the inertial rate, so in inertial range, so we can write the same ratio for the energy and for the cross-helicity. And in general, the characteristic time for cross-helicity transfer can of course be different from the time of energy transfer. So we can write the similar formula for both transfer process. In this graph, I show directly how this characteristic time depends on scale. And in black are shown the turnover time. So the first result is with the typical time. This is for the case when the cross-helicity input is 0.6. And you can see that this characteristic transfer time is more as 10 times larger as the typical turnover time. And the next very interesting result is that in the inertial range, because here the flux is constant, so the scaling law for the time should be the same as the scaling law for the energy. But what is interesting, exactly the same scaling law is visible not only in the inertial range, this is the end of inertial range shown following the constant flux, and the same law is visible up to the smallest dissipative scale. What about the turnover time? We can see the corresponding law in the inertial range, and the change of the slope is what is typical in the near the dissipative range. And the last graph shows that the correlation coefficient defined for each scale is constant inside the inertial range, and then it goes down. Here it maybe was not a good idea to show it in the logarithmic scale, and it shows with its unity. It's not unity, it's something about 0.8 in this case, and it means that the both reduction coefficient for the energy and for the cross helicity follow the same laws, but there are some constant ratio between the both, which is visible in this graph. So this is the second fact, which seems to be really quite interesting, because some kind of extended self-similarity is obtained here. So this scaling law, which is quite evident for the inertial range, is extended up to very small scales in the dissipative edge. It's all.
We have time for a couple of questions. David?
What's the magnetic front number?
The magnetic front number is 1. Reynolds magnet, the both Reynolds number are 10 in power 6, 10 in power 7.
Well, if the magnetic front number is not 1.
No, 1, I said.
If it were not 1, how does it
I don't think that some dramatic change will arise, because we have played with the magnetic front number enough. The inertial range is long enough, so of course we will have some changes in small scales, but what we were interested to look in the inertial range, I think it's easy to check.
What's the physical reason of increasing of the T n? What actually happened? Something happened?
To my mind, it means that because you have the alignment of magnetic field and velocity field, yeah, it means that the turbulence is strong enough, so the vortex can rotate very fast, but this rotation cannot result in nonlinear transfer, because in the equation you have U grad U and B grad B, and they compensate one the other.
It's more or less understandable, but my feeling is that something should be happened with viscous cutoff too, gas. If not, you cannot produce inertial range at all.
You mean that the question is the dissipative scale the same or not?
Yes.
In our calculation, it does not change strongly.
Bad news in this sense.
For whom?
For you.
Yes. Did you plot your results in terms of SSR variables? Because as far as I remember, we predict, or we got some power law prediction for the Z and Z minus spectra.
We have not tried.
Because something like the sum of the exponent has to be 3 or something like that. 3 half plus 3 half and right. Maybe I don't remember well, but I think
We have not, because we have not idea why something should be more clear in the exact variable, so we have not done that.
So definitely in presence of strong magnetic field, there is something like that happens. The sum of exponents is equal to -4, this solution, which means that's right. But here is no external field. So
No external field.
how you find the, how you separate which is which, you know?
I've not understood. It's a question or it's not a question?
No,
I think it's just
Exponents.
Okay. Anybody else? Okay, let's thank Peter again, all the speakers.